Uniform circular motion is the analysis of an object as it spins. This spin can either be a rotation, which would be a full object rotating around a central axis, or a revolution, which would be an object rotating around an external axis, like the moon going around our planet. In either case, the uniform characteristic of circular motion for our case will be that the velocity directed tangent to the path will not change as the object spins around that particular rotation or revolution. Before we can dig into some of the other components of circular motion, we just need to make sure that we're clear on some of the basic terms, which of course, from the center out to the location of the point in question, in this case a ball being spun around, let's say on the end of a string, the distance from the center would be radius. Obviously, the distance traveled around the outside is the circumference, which you should know the formula is 2 pi r. It's important to note that the velocity component is perpendicular to the radius, which indicates that it's tangent to the path. Since it is uniform circular motion, the velocity value does not change, but the direction does. So if I look at a point somewhere further along on the path as this spins, the velocity would now be directed tangent to the path here with the same speed in a new direction, v. Right? And so constant speed moving around the outside. Other terminology that we should be familiar with based on our analysis of waves is period. Period is given the variable capital letter T, which is the time for one rotation or revolution. Right? The time it takes to go around once. As we've seen previously as well, in waves, frequency, which is lowercase f, is the inverse of period, but also would be defined as the number of spins per second, which if you track the units would cause frequency to have a unit of inverse seconds, 1 over s, which in some cases is presented as s to the -1, but this also has its own name, which is called hertz, Hz. So each one of these represents the same unit for frequency, keeping in mind that, of course, period will be measured in the SI unit of seconds, s. Given this information, generating the equations for uniform circular motion is not too difficult, because if we think about our v equals d over t formula from before for velocity, v equals total distance divided by total time. In this case, we are not using the vector notation because the velocity is actually changing as this system is going around, but the speed is staying constant. How is that possible? It's changing direction. It was going this way, now it's going that way, then it's going this way, and so on around the circle. And we'll get to acceleration in just a second. If we consider the fact that the total distance around the entire circle is the circumference, and the total time it takes to go around is the period, then we can substitute in our values for circumference as 2 pi times the radius, and then divided by the period. So the velocity formula for uniform circular motion is 2 pi r over t. And then due to the inverse relationship to frequency, this can also be written as 2 pi rf. And you'll see this on your equation sheet, one or the other generally. When we consider the fact the object is accelerating as it goes around, the acceleration is referred to as a centripetal acceleration. And it's important to recognize that centripetal acceleration literally means center seeking. And if we consider the diagram above, as the velocity changes direction going around this circle, this object moving from this position here to this position here has been pulled in towards the center of the circle. This vector that is perpendicular to the velocity and parallel to the radius is the vector direction of the acceleration. This acceleration is a vector that we consider to be a standard direction that would be consistent around the circle. Obviously, here it's down and to the left, and here it's more down and to the right almost. But we label this as a vector that remains with a consistent direction because we're going to define the frame of reference within a circle for acceleration as going towards the middle as positive. And so it's a unique characteristic to circular motion to use an FOR for the radial direction as going in as positive. All right? It's important to recognize that this is pronounced centripetal, P-E-T-A-L, and not centrifugal, F-U-G-A-L, which means center fleeing, and is not a thing. There is no such thing as a center fleeing physical characteristic. We'll address that more when we talk about forces. For now, we're just focused on the basic motion, the motion of the circle. So as this thing is spinning, the velocity is changing direction, the speed is remaining constant, and the acceleration is remaining constant. The acceleration points towards the center and has a set magnitude value, right? This value can be calculated relatively simply, right? We describe this as a centripetal acceleration, so we're going to add a subscript C to indicate centripetal acceleration, and this would be the velocity, the linear velocity that we've identified above, right? Linear as a non-vector divided by, v squared divided by the radius. This is the standard formula for centripetal acceleration. Please notice that this is a vector, but in this formula, these two are scalars because they represent the magnitudes. And so this directional characteristic comes from an understanding of uniform circular motion and is identified by you, not by the other terms in the formula. Substituting through, you can simplify this formula or derive more useful formulas by substituting in formulas over here. So if I put in 2 pi r f and I square that divided by the radius, centripetal acceleration simplifies to be 4 pi squared f squared times r. And there's lots of different uses for doing this. Obviously here, if I didn't know the speed, but I knew the frequency, I could calculate the acceleration nonetheless. In all cases, these are going to use standardized units, so as long as we're using the units identified above, velocity will be measured in meters per second, and acceleration will be meters per second squared, as we expect.